Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about levers. So as a kid, you probably figured out the fundamental idea behind levers when you went to the playground and you were on a teeter-totter. You figured out fairly quickly that if you had two kids on that teeter-totter and one kid was bigger than the other kid, that bigger kid would move in closer to the pivot point, which is called the fulcrum, and the lighter kid would stay as far away as possible just in order to balance that teeter-totter. So that's what we're going to be talking about with levers. We're going to be talking about the relationship between forces and distances in a lever. I'm going to call the input force effort, and I'm going to call the output force load. There are three classes of levers depending on where the fulcrum is located. Another concept that we need to understand with levers is the distances. So the distance from the effort to the pivot point is called the effort arm. The distance from the load to the pivot point is called the load arm. As I mentioned, as a kid, you figured out that the bigger the kid, the less distance he should be or she should be from the fulcrum. When you have two quantities that as one value increases, the other decreases, you have an inverse proportion. And I've talked about inverse proportion previously. We learned that to set up an inverse proportion, the products are equal. So in this case, if I call effort E and effort arm EA, if I call load L and I call load arm LA, the product of the effort and its distance to the fulcrum will equal the product of the load and its distance to the load arm. So that formula can be written like this: effort times effort arm equals load times load arm. That relationship is going to be true whether it's a first class, second class, or third class of lever. Another concept I want to talk about with levers is mechanical advantage. Mechanical advantage is always defined as load over effort. We talked about mechanical advantage in the previous video on hydraulics. So mechanical advantage is always defined as the output force divided by the input force. However, we can use the lengths of the effort arm and the load arm to calculate mechanical advantage as well. But remember that because the lengths are inversely proportional to the forces, if we're going to use them to calculate mechanical advantage, we have to flip the order. So with a lever system, we can calculate mechanical advantage by taking the effort arm and dividing by the load arm. You will only get mechanical advantage if the effort arm is longer. This might seem a little bit confusing, but when we get into examples, we'll calculate the mechanical advantage using the forces and using the effort arm and load arm, and you'll see that this works out. So let's get started with first class lever. So first class lever is one in which the pivot point or the fulcrum is in between the effort and the load. We talked about the teeter-totter. We know that the distance from the effort to the fulcrum is called effort arm. The distance from the fulcrum to the load is called load arm. So there are a number of different tools that you probably use that are first class levers. For example, if you have wire cutters, the pivot point is right here. So the distance from the handle where you're grasping the handle to that pivot point would be the effort arm. The distance from that fulcrum to where you're cutting would be the load arm. And the longer these handles are, the more mechanical advantage you'll get. So that's an example of a first class lever. Using a pry bar or a crowbar is a first class lever. Using a hammer to pull out a nail can be thought of as a first class lever, and so on. There's many examples of first class levers. We know the relationship is effort times effort arm equals load times load arm. So let's take a look at an example. We're using a screwdriver to pry off the lid of a paint can. The distance from the blade of the screwdriver to the edge of the can So we're using a screwdriver to pop off that paint can lid. The distance from the blade of the screwdriver to the edge of the can is 3/4 of an inch. The distance from the edge of the can, which is our fulcrum, to the handle of the screwdriver is 15 inches. So the distance from that pivot point to where my hand is 15 inches. What effort is required if a force of 120 pounds is needed to pry off the lid? And second, what is the mechanical advantage? In order to solve this, you could write the 4 values at the side. What effort is required? So we don't know this. The effort arm will be the distance from where the effort is applied to the fulcrum. So that's where your hand is to that pivot point, which is 15 inches. The load is 120 pounds. And the load arm is the distance from the fulcrum to the edge of the screwdriver, which is 3/4 of an inch. I'll just change that to a decimal, 0.75 inches. I can plug these values into my formula. So effort, which I don't know, times my effort arm of 15 will equal load, which is 120 pounds, times load arm of 0.75 inches. So the effort and the load will both be in the same unit of pounds. These distances have to be in the same unit, in this case, inches. We can multiply 120 times 0.75 and then divide by 15 to get E by itself, and we get 6 pounds. So we only need an effort of 6 pounds at the handle to create 120 pounds of force on the paint can lid. The second question says, what is the mechanical advantage? I can calculate this 2 ways. I can use the actual forces to find it. So my mechanical advantage, which is load over effort, would be the load of 120 pounds over an effort of 6 pounds, and that would be 20-to-1. We typically write mechanical advantage as something to 1. If you hear that the mechanical advantage is 20, the assumption is it's 20-to-1. So remember, if you are using the lengths of the effort arm and the load arm to calculate mechanical advantage, it's not this same order. You have to invert it. So it's going to be the effort arm divided by the load arm. So in this example, my effort arm is 15 inches. The load arm is 0.75 inches. And if you divide 15 by 0.75, you get a mechanical advantage of 20-to-1 as well. So either method should yield the same mechanical advantage. Let's take a look at second-class levers. A second-class lever is a lever where the fulcrum is at one end, effort is at the other end, and the load is somewhere in between. People often think of wheelbarrows. If you lift up the handles of a wheelbarrow, your pivot point will be the wheel, and the load is in between your effort and that fulcrum. Another example would be a nutcracker. You'll also often see second-class levers going into a hydraulic system. With a second-class lever, you're going to get the maximum mechanical advantage because the effort arm, which is the distance from the effort to the fulcrum, is going to be the whole length of the lever. The load arm will be the distance from the load to the fulcrum. The relationship still holds. Effort times effort arm equals load times load arm. Let's take a look at an example of a second-class lever. Our example says a weight of 500 pounds is raised with a 6-foot-long pry bar used as a second-class lever. So when we use a pry bar, if the fulcrum is in between the effort and the force, that's a first class. But if our pivot point is at the end and the weight is being lifted between the effort and that fulcrum, then it's acting as a second-class lever. So that's what we're dealing with. We're putting the weight in between the fulcrum point and the effort. The question asks, where should the weight be placed if the effort is 75 pounds? And then secondly, what's the mechanical advantage? So again, you can take a few minutes to write everything out. So effort is 75 pounds. We are lifting 500 pounds, so that's our load. The pry bar is 6 feet long, so that's the total of our effort arm as well. So our effort arm is 6 feet, which we might want to change to inches. And we want to find the load arm. We want to know how far that weight should be from the fulcrum. Now that we have all of those established, we set into our formula. So we're going to have 75 pounds times 72 inches equals load, which is 500 pounds, times load arm, and that will be in inches if this is in inches. So we take 75 times 72 and we divide by 500. When we solve, we get load arm equal to 10.8 inches. If we would have done it in feet, we would have had 0.9 feet. So just be aware of the unit that you're using and understand that both of these lengths have to be in the same unit, just as both of these forces have to be in the same unit. Now, in order to calculate mechanical advantages, I could use the forces. So mechanical advantage will equal load over effort. So that's 500 pounds over 75 pounds, which is 6.666 repeating, so I could round that off, depending on how many decimal places you want to go. We could check the mechanical advantage by taking the ratio of the effort arm to the load arm. So effort arm is 72 inches, load arm is 10.8 inches, and when we do that division, we also get 6.7 to 1. Now let's take a look at third-class levers. Definition of a third-class lever is that we have the fulcrum at one end and load at the other, and the effort somewhere in between those. So in this case, the load arm is the distance from the load to the fulcrum, so it's the total length, and this will be the distance of the effort arm. Examples of third-class lever would be tweezers, cranes, backhoes, certain type of barbecue tongs. And what you might be aware of is that you're not going to get mechanical advantage with a third-class lever. The effort that's required is more than the load. However, what you lose in force, you will gain in distance. Once again, we have the same mathematical relationship between the forces and the lengths of the arms. Effort times effort arm will equal load times load arm. Let's take a look at an example of a third-class lever. So our third-class example says an effort of 100 pounds is being exerted in a third-class lever. The length of the effort arm is 5 inches and the length of the load arm is 20 inches. What is the load? And what's the mechanical advantage? Let's relate this to fishing. We have our fishing rod in our one hand, and that acts as our pivot point, or we have it in a fishing rod holder. Our effort is 5 inches from that pivot point, and our fish is at the end. So that's our fish is our load, and here's our effort. So if we need to exert 100 pounds to lift up that fish, how big is our fish? So again, we can take a few minutes to complete our values. Effort is 100 pounds. Effort arm is 5 inches. Load arm is 20 inches. And we're finding load. Then we plug our values into our formula. So we have 100 times 5 will equal load times load arm is 20. Divide both sides by 20 so that we get load equal to 25. In order to calculate mechanical advantage, I could either use the two forces. So I have a load of 25 pounds divided by an effort of 100 pounds. So we could write that as 0.25 to 1 or 1 to 4. As I mentioned, it's not an advantage, it's a disadvantage. Or we can use the ratio of the arms, which would be 5 to 20, which is 1 to 4 or 0.25 to 1. The nice thing about levers is it doesn't matter what class of lever it is, we're working with the same formula.